Hello, welcome to the Fast Querying webinar. I'm Muthu Chinnasamy. I'm a senior solution architect at MongoDB. Before I start the webinar, a couple of things. This is a fairly large presentation, so a lot of material to cover. If you post your questions in the chat box in the bottom left corner, we'll try to answer them as we go along. And then if there are any leftover questions at the end, I'll try to answer towards the end. So here's an agenda of the webinar, what we are going to cover. So let's quickly get into the introduction. So MongoDB is uniquely positioned in the marketplace for databases. So traditionally, RDBMS technologies, they are quite strong in offering a strong consistency model and offering a wide range of secondary indexes in addition to primary keys, and also provide you a powerful query language. Whereas in the NoSQL world, they offer a flexible data model, scalability and performance. And MongoDB is uniquely positioned in this market, combining the best of both worlds from RDBMS and NoSQL. In this webinar, we'll be focusing on the secondary indexes and the indexing features that are available in MongoDB and how you as customers can take advantage of the indexing features to drive the most performance of your MongoDB installation. Before we go into the details, when to use an index. So basically, indexes are very powerful in driving performance, and they are the single most tunable parameter available to you. With less effort, you can drive the most value. So you would use, based on your data access patterns, the most frequently accessed queries, and also those queries where you want very low latency response time, you would use indexes. And if your goal is to get all the records from a collection, for example, indexes are not probably the good choice because you would have to read the index and then you have to read the collection. That's double the work. So how different are indexes in MongoDB? So some other NoSQL technologies, you would have to create a view in front or a materialized view that will have to be used by the application code or some kind of MapReduce job that needs to be run. Unlike any of these, in MongoDB, these indexes are created with a command, and once the indexes are created, whatever operation you perform on a collection, the operations are also atomically done with the index. The code, application code, or developers do not have to do any additional actions, and MongoDB does all the work behind the scenes. So what is fast querying? So I will walk you through an illustration of a hypothetical situation where I am presented with a query, a question, a business question, where I need to provide all the zip codes in the New York City, in the state of New York, where the population is more than 100,000, and in descending order of the population results. So in MongoDB, my query would be what's highlighted in green. So I'm looking for state New York, city New York, population greater than 100,000, and I'm sorting by population. The -1 is for descending order. So in my data set, which is basically available on media.mongodb.org, it's a zips.json collection. I'm just showing the output for brevity. I left out a couple of other fields like _ID, but I would expect to see 2 documents out of a collection of 29,000 odd documents in there. So suppose I do not have any index on this collection. What does MongoDB have to do in terms of its own internal work before you see the output? So for now, I'm showing the observations. I will illustrate on how to view these observations. For now, let's focus on the results. The cursor, basic cursor, means I will not use an index here. This is like a full table scan in a RDBMS parlance. The N2 means the number of records returned to me as an output. And the N-scanned objects is number of documents MongoDB has to visit. In this case, it's 29,470, which happens to be the total set. So the N-scanned is number of index entries or documents In our case, since we did not use any index, it happened to be all the documents visited. So millis is the number of the milliseconds that MongoDB took to display the output. In this case, it's 12 milliseconds. But still, a whopping 29,470 documents have to be scanned just to return 2 documents as output. So what happens? I define an index. So I create the index using the syntax in green. So I create on the state field in ascending order. So I rerun the same query which we used before. In this case, MongoDB did use in the index that we just created. So we confirm that with a B-tree cursor. B-tree cursor means an index has been used, and which index is used, it shows state_1. So that index is being used. Same parameter, and I wouldn't expect any different. 2 documents returned. The scanned objects, though, went down to just 1596 from 29,470. That's a dramatic improvement. And unscanned in this case, since we used an index, 1596 index entries are used. So now our milliseconds gone down to just 3 from 12. So can we do better? So I can define an index on multiple fields. So let me add another field to this index in city in ascending order. The syntax is shown green. So with this, my observations are I'm still using an index, but this time MongoDB picked the state and city compound index. And then my documents returned is still 2, but the scanned objects, which is indicating how many documents visited in producing the result, is gone down from 1596 in the previous single field index to just 40. And the nscan, which is how many index entries I visited, is down to 40. And my millisecond response is now 0. In MongoDB, it's granular to the milliseconds, but if you have application code, you can see the granular how many microseconds was used by this query. But I'm not happy with this. Can I further tune this? Sure, I can add one more field to the compound index. Let me add the population to the index. So I create a new index now, state, city, and population all in ascending order. So now I rerun my query, and my observations are still MongoDB picked up the new index, which is a good thing, and it used the index state, city, and pop, and it's using a reverse order because in my query, I am sorting the results by population in descending order. So MongoDB can traverse indexes forward and reverse in both directions. In this case, it happened to traverse reverse to satisfy my requirements. So my number of documents returned is still the same, but the number of scanned documents is down to just 2, and the number of index entries I visited is 2 to satisfy the 2 documents I returned. This is fast querying, folks. This is how I would tune my application. And my milliseconds is showing 0, but if you use a Java program, for example, you can really report the lower granularity or time units. So how is this possible? In MongoDB, indexes use B-tree structure. So if suppose I create an index on a field A in ascending order, MongoDB creates buckets, and there are in each bucket, if you will, there's a key node and there's key data. The key nodes fill from left to right, and the key data fills from right to left. And the buckets in this case happen to be -infinity to 5, and 5 to 10, and 10 to infinity. And the leaf nodes go, they split once the bucket is full. They have a 24 byte limitation, at which point the bucket splits. And the bottom, you will see the collection where each curly brace is a document. Okay, so if I run a query where find all the matching documents where A equals 7, then since I have an index created, then MongoDB has to just look up the bucket and then traverse the red arrows from top to bottom, where it needs to just scan the index entries and then straight to the location in the collection where the matching document is found. If I didn't use an index in this case, then you would follow the red line at the bottom where the collection has to be scanned from the beginning till the end. So finally, now that we know indexes help performances dramatically, and particularly compound indexes to satisfy your data access patterns, one would be intrigued to create multiple indexes. But there is a word of caution there. Do not create multiple indexes. If you have too many indexes that are not used by Mongo, they consume space. And they also they affect your write operations, because MongoDB has to maintain for each write operation the associated indexes as well. How do I drop indexes once I confirm the good indexes are being used? I do not want the unnecessary indexes, then I use the drop index command with the syntax shown in green in this slide. Another technique strategy used to fast querying is to use projection. So in MongoDB, you can limit the number of fields that are returned to your client application. That will reduce the number of bytes that are placed on the network and the amount of memory that's consumed by your client application. The way to do is, I will go to the illustration in the box. So if you just focus on the blue highlighted, where in this case I am saying item 1. 1 means enable this field in the result set. And quantity 1, so these two fields, I'm enabling them to be returned, and I'm suppressing the _ID field, which is always returned if it's not explicitly suppressed. So in here we are giving a 0 instruction to exclude the _ID in the result set. So this is an example of inclusion. The next example is an exclusion. So I'm saying type 0. So just leave out the type field, but return to me everything else, every other field. And inclusion and exclusion are mutually, other than the _ID field, you cannot combine inclusion and exclusions. And in case of an array, there are only 3 options that are available: the $operator, the $lmmatch, or the $slice operators. So in this example, we are using $slice too, so meaning just return the first 2 elements of an array, even if the array has 10 or more elements in it. So now, combining the features of indexes and projection, we can enhance further queries that can be satisfied by an index only, meaning I do not have to access the underlying collection if what I'm querying can be satisfied by the index, and I use a projection to suppress the _ID. Remember, the _ID is always returned in MongoDB, so you'd have to explicitly suppress it. So in the example there, this is a user authentication collection, so I store user information and the password. So in my query, I'm given a user, but all I need is to get the password and then validate with what the user has inputted. So in this example, I'm suppressing the _ID. MongoDB will use just the index. It doesn't have to access the collection. This is further enhancing your response time. And finally, there's the concept of working set, where all your active indexes and active portion of your data combined together, they're called working set. Maybe you started your application today with a known workload, and it picked up more volume. Your data set grows over time. So as your data set grows over time, your working set also grows over time. And your MongoDB node has a finite amount of physical RAM on that server. So once you reached a point where your working set is bigger than your physical RAM, then you have 2 options to scale your installation. You can add more memory to the existing node, and there is a limit to it. And then you can do sharding by scaling out, by having more sharded nodes, and then thereby you can increase more RAM available to your application. So now that we know fast querying can be done with a variety of techniques, including indexes and compound indexes, projection and covered queries, let's explore what MongoDB offers in terms of index types and their properties. Some indexing basics. So you use the ensure index command with a JSON document to create an index. In MongoDB 3.0, the ensure index is deprecated. Start using the create index command. So now ensure index is an alias to create index command. If I want to create in a descending order, then I specify a -1 in the JSON document to a given field. Suppose my field is an array and I have multiple elements and I want to create an index. No problem. These are called multi-key indexes in MongoDB. So in this example, I'm using tags field, which is an array, and I just say tags ascending order. Each and every element in the array will be indexed when index entries are created. You use the get indexes command to find out on a given collection what indexes have been created, and then you can add missing indexes or drop unnecessary indexes. In MongoDB, on the right-hand side, I have a box where I have sub-documents for an article-based application. So multiple authors write articles, and I would like to know for a query which articles have more than 150 comments in a given day. So my query looks like what's on the bottom. So daily.comments using the dot notation, I'm looking for greater than or equal to 150. So in this case, to help the query perform better, I may want to add an index, daily.comments, so that dot notation is supported in MongoDB to add an index on a subdocument field. Compound indexes we have seen in the illustration earlier. So these can be created with multiple fields separated by a comma in your ensure index or create index command. So in this example, we are creating a compound index on two fields, author and tags, both are in ascending order. Then I can query, when my query has all the fields in the index, then the index will be picked up. Or if my query has the leading column of the index, in this case author, the index will be used. If I happen to use the non-leading fields in the query, then MongoDB will not be able to use that index. This is something to keep in mind. So now that we have a compound index, you don't have to create a separate index on a single field, author, because it's already a leading field in the index. So you don't have to explicitly create another one to save space and to save on write performance. So in terms of sort order, indexes can support sort order. In a single field index, the sort doesn't matter. You can create ascending or descending. And MongoDB has the ability to traverse an index in the forward or reverse direction. But sort order does matter in compound indexes. So in this example, the index is created with author and date in descending order, author in ascending order. So MongoDB can use the index to satisfy queries that want to sort by date descending order. So the in-memory operation to do a sort once the documents are retrieved doesn't have to be done. That's further tweaking for your application. There are some additional options that MongoDB allows. So you can enforce uniqueness. So meaning if you don't want duplicates in your collection, then you can enable on the set of fields that define uniqueness, and by giving the keyword unique true in your create syntax. So once it is created, MongoDB will reject any attempt to create duplicate records. Combine that with sparse indexes. So basically, if MongoDB supports a flexible data model, so meaning I can have documents that may or may not have certain fields. And if I want to create an index on a field that may or may not have a value in the document, I can use the sparse index option in the create syntax. Without the sparse, when a document is encountered where the field is not present, then MongoDB will store it as null in the index, in the key data section. But if you create with the sparse, the index will not have the null entry. So by default, MongoDB builds indexes in the foreground, but the foreground index is a blocking operation. So customers can use background index builds to create them without blocking your other operations. You can also build more than one index concurrently using the background. The most popular option to choose the background index build is on your secondary in a replica set. You would basically take your secondary into a standalone mode, build the desired index in the background mode. Once it is built, bring it back into the replica set. One thing to keep in mind is you wouldn't want to exceed your oplog window. If your oplog is rotated, by the time your index is created, then you will have to reinstantiate your secondary. So you will want to either make the oplog big enough to cover the time it takes to build the index, or take necessary precautions there. There are other index types in MongoDB. I'm going to go over geospatial indexes and text indexes in this webinar. So what is a geospatial index? So on MongoDB supports storing GeoJSON documents and then querying based on GeoJSON documents. It can be on a Euclidean plane coordinates, or it can be a spherical coordinates. So when you create an index, at the bottom of this slide, there is a 2D sphere. That's the keyword you specify in the creation command for the location field, indicating to MongoDB this is a spherical coordinates that will be used. So you have the geolocation.getCurrentPosition in most of your HTML5 APIs. You get the geolocation, the longitude and latitude, and once you have that, you can provide that to your application while inserting a record into MongoDB or while querying data from MongoDB. So let's say I have a mobile application. I stored various points of interest amenities into my MongoDB collection. Now I want to query based on mobile user base, and the way I do is use the HTML API to get their current position, get the longitude and latitude, and then form a geospatial query like in the example here with a $near operator. So $near operator does proximity query. In this example, we are looking for point coordinates with the coordinates there, and also using the $max distance parameter. These are specified in meters. So I'm looking for all the points of interest in a 5,000 meter radius. Another feature that's enabled by default in MongoDB are the text indexes. So text indexes, you can at most create one for a collection, and these can be very large because these are similar to multi-key. MongoDB has to index a lot of values in the text to match the text index searching. You would use the $text query operator to search in a text index. There are a variety of ways you can create. You can combine multiple fields. In the example on the right-hand side box, you create a text index on title and content fields. You can also use the $operator to index all the text fields in a collection. Or you can change the weightage to change the importance of the fields. Like for example, title I'm giving a 10% weightage, and content I'm giving a 5% weightage in the third example. So once a text index is created, the way I query is using the $text and $search operator. In the first example, it's a plain search for keywords MongoDB. In the second example, I'm also scoring with the $meta operator. So once I have this output, then I can sort by the $meta to show what are all the most relevant searches by the scoring. So this slide is a recap of some of the things that we already talked about. One of the things that we didn't talk about is the absence of values and negation. So if you have a query where you're looking for not equals, or where you don't have a value in that field, possibly, then MongoDB cannot use an index. This is something that you want to be careful. In this slide also, I have a couple other things to indicate here. If you have low cardinality fields where there are a lot of repeating values, then you may want to use caution because MongoDB has to do a lot of index entry scanning. If you have the choice of a highly selective field, I would place it first in your compound index or index based on those fields for fast querying. And we have talked about eliminating unnecessary indexes. Another thing of particular interest is when you use regular expressions, you may not want to use something like, it has to be rooted to the keyword. So if I'm looking for all first names that start with A, then I would want to use A and then the wildcard, in which case MongoDB will use an index. But if I start looking for, show me all the first name that end with a specific character, then wildcard and then followed by, let's say, Y at the end, in which case MongoDB may not be able to use an index. So since this is a big topic, schema design has to be done properly and the right indexes have to be done. We recognize at MongoDB that customers may need help in getting their application done properly from the ground up, and the schemas done properly, all the right indexes are done, your data access patterns are properly reviewed, and then the best performing queries are implemented. MongoDB does offer a rapid start consulting service whereby our consulting engineer is available to help with the customer on site up to 4 days and then provide a written recommendation and output within 10 business days to help you move along faster. So now that we know what indexes can be done, there is a special feature in MongoDB that's called index intersection. Let's go through this scenario. So suppose I have a compound index on status and order date in descending order, and I have a query that's highlighted in blue, and the query is by order date and status equals A. In which case MongoDB should be able to use this index, because all the fields of the compound index are used in this query. And another scenario with the same compound index, I'm querying based on status equals A. This query will also use the compound index that we defined because status is the leading field in the index. So what happens, I want to query by just the order date. It's not the leading field in the index, so MongoDB will not use the index. And another scenario, I want to retrieve all the fields, but I want to sort by order date in the ascending order. MongoDB will not be able to use the index in this case because it's defined in descending order, and we are trying to sort by ascending order. And since we are returning all the fields, MongoDB will not be able to use this compound index. So this is where index intersection come into picture, where all the 4 scenarios we looked at can take advantage of the index intersection feature. So to be able to use this feature, instead of the compound index on status and order date fields, you would create 2 single field indexes, one on status field and one on order date field in descending order. So when MongoDB goes through its query optimization, when a query is submitted, it may or may not choose index intersection. So it really depends on your data set and your data access pattern. So in the example on the ZIPS collection, I did not get index intersection to work, but I found evidence MongoDB tried to use index intersection. The way to find out whether index intersection was used or not is to look for the stage and_sorted or and_hash. So one of these meaning MongoDB tried evaluating this index intersection. If it proved to be costly, then MongoDB will not use. But on the other hand, if the intersection was found to be an optimization, then more or less MongoDB will use that feature. So I create my indexes. How do I make sure whether an index is effective or not? So I showed you guys a lot of observations like N or N-scanned or N-scanned objects. How do I get these so I can measure whether an index is effective or not? So in this section, we'll go over those. So the query optimizer is the first element in MongoDB that for each type of query, it periodically tries all useful indexes. And then it collects data into various buffers. I wouldn't go into the internals of how it does, but just keep in mind the one that fills the buffers fastest based on a batch size, that is the winning plan that MongoDB will cache. And the winning plan is temporarily cached up to the point when the collection used 1,000 write operations, at which point it will try to reevaluate. Or when you try to add or drop an index, again, the plans will be reevaluated. If your MongoDB goes down and comes back up, the plans will be reevaluated. Same with the command like reindex. As of MongoDB 2.6, the index intersection feature can try to use multiple single field indexes to fulfill queries. And the way to evaluate queries is the explain plan. This is similar to explain plan available in most mature RDBMS. So this is how you use to evaluate whether an index is being used or not, how many documents are scanned, how many objects are scanned. On the MongoDB console, you would use the same query with a .explain at the end. The .explain method is the one that's going to return, among many other things, key metrics such as the number of documents returned, number of index entries scanned, whether an index is used or not, which index is used, and whether the query was fully covered, meaning I didn't have to go to the collection, all my data was retrieved from the index itself, whether an in-memory sort was performed or the index was able to provide the results in sort order, how long the query took in milliseconds. So here's an example I have in the box where no index is used, so this is a collection scan. The way I identify is by the keyword in the cursor section. It shows basic cursor. That means it's a collection scan or full table scan in RDBMS parlance. The N12 is the number of documents returned. N-scanned objects is the number of documents that had to be scanned in the collection. N-scanned, it could be the number of index entries scanned, or it could be the number of documents scanned if there is no index. And index only is false if this is an indication of a covered query, and the millisecond response time. In case MongoDB uses an index, it changes to something like this, where the cursor shows, instead of basic cursor, you would see a B-tree cursor. All other parameters explain the same meaning. So there are other types of cursors. When you use the geospatial, you will see a geosearch cursor. When you use a text index, you would see a text cursor, and so on. So recently, MongoDB made 3.0 version generally available. So in this release, a lot of improvements have been done, including the explain method. By default, explain method will not run a long-running query. Suppose your query takes a very long time. Previously, MongoDB used to execute before giving the output of .explain. Not anymore. If you want to know whether an index is being used or not, simple information, your .explain will give query planner information only. To see more detailed information on, for example, the execution stats, what are all the plans considered, you would tune up the verbosity level by using explain within parentheses. You would use the keywords execution stats or all plan executions. And also in 3.0, MongoDB changed the way some of the fields are described in the explain plan output. So no more you see N, you will see an explicit N returned, meaning the returned documents. And also the millis becomes execution time millis. And index entry scan becomes, the N scanned is now displayed as total keys examined. The N-scanned object is now shown as total docs examined. So this is more meaningful, more intuitive to someone doing this exercise. Oh, I'm querying now two keys. I'm querying two documents instead of having to decipher what the nscanned and nscanned objects. And it also has a clear index name in lieu of the cursor that we saw before. Other improvements in 3.0 for explain plan is fine-grained query introspection. So now the various stages are shown. So for example, sort stage is shown as a separate section. Additional commands are supported in 3.0 like count, group, delete, and update. These commands can be explained now. And also there is a db.collection.explain method, and then you chain the find or other query modifiers at the end. So the advantage of this is it returns a cursor to the explain result. Now you can use the .next method to return the results like it's shown in the example. Another feature that can be used to evaluate your running application is the database profiler. So this is actually collecting actual samples from a running instance of MongoDB. This is tunable for the level or slowness or both. And it can be controlled dynamically, so you can switch on to collect some telemetrics and then switch it off. And then once you have the data, you can review and then take performance tuning options. How do I implement this? So by default, MongoDB flags any operation that's more than 100 milliseconds to the MongoDB log. To find out whether a profiling is used or not, you would use db.getProfiling level, and it will show you what level is being used, what is the configuration for slow ms, slow milliseconds. If you want to set, I want to find out operations that are more than 50 milliseconds, then you would use like in the example here. The various levels, 0 is off, 1 is give me slow running operations, and 2 basically show me every operation in the output. And the raw data is stored in a collection system.profile, and you can query db.system.profile, and then you can look for specific namespaces, specific queries to find things of interest to you to do more on performance tuning exercise. So now that we have done most of the 2.0, 2.6 version and before index features, what's new in MongoDB 3.0 specific to indexes? So in MongoDB 3.0, dramatically enhanced the way it stores data on the storage devices. So now customers have the option of choosing storage engines. So previously, the storage engine, the only available option to store data was mmap v1. So now we have additional option in WiredTiger. So WiredTiger significantly improves performance, and it also compresses data on the fly. But to specific improvement for indexes is you can choose where to place your data in indexes. When you start your MongoDB, you would specify along with DB path, you would specify additional parameter called storage engine with the keyword WiredTiger. That is, you are instructing MongoDB to use the WiredTiger storage engine instead of mmap v1. And you additionally specify a command option WiredTiger directory for indexes. When this is specified with the WiredTiger storage engine, MongoDB stores all collections under the DB path in a collection subfolder. Each collection will have one file. And for each index, you will have a file created under DB path/index subfolder. So now you have the option of placing the collection on a different disk subsystem and your index on a different disk subsystem. For example, you may want to place your indexes on a SSD for higher performance. WiredTiger also supports a variety of compression to suit the needs. So by default, indexes are compressed using the prefix compression algorithm. So you don't have to specify, although I've given an example here in green, is the command line option to use when starting MongoDB. The index compression is on in WiredTiger by default. The indexes are on disk are compressed using prefix compression, although at creation time you could choose a different block compressor like a Snappy or zlib that's available in WiredTiger. So this not only compresses the indexes on disk, but when the data is retrieved, the compressed format is also saving you precious space in your RAM. So with these changes in 3.0, MongoDB offers fine-grained control for DBAs. By having the WireTiger storage engine, you have wide use cases to support, specifically more write throughput use cases. And like we saw in the example, you can place indexes on faster storage devices depending on your application use cases. And you can use specific index compression, saving disk and RAM capacity. If you have more CPU capacity, then you can go as high as zlib compression to save the most space and most capacity. And you have finer compression controls for creation time for collection and indexes. For different indexes and different collections, you may choose a different block compressor. For example, archive data, I may not use that regularly, but it compresses very well. I may choose zlib for that kind of data. So I can come up with a data lifecycle management by choosing different compression needs, and then cold data I may place on archive storage or slow storage. The options are unlimited for your DBAs and ops teams. So with this, we conclude this webinar. We hope you enjoyed the webinar. So we value your feedback for tweaking our presentations in the future. So please take some time and share your feedback, and we value them. Thank you very much.